Okay, I'm going to go through the answers to these questions. So the first question is talking about alkene E and the fact that alkene E has restricted rotation because it has both a sigma and a pi bond. And then it asks to describe one difference between a sigma and a pi bond. So when you're doing that, you have to mention both the sigma and the pi bond and what the difference is. So I've got two possible answers here because it's a 1-mark question. So you could have said that for a sigma bond, there's a direct overlap of orbitals, whereas for a pi bond, it's a sideways overlap of p orbitals. Okay, a sigma bond is either the direct overlap of s orbitals or p orbitals, whereas pi bond is sideways overlap of p orbitals only. Or you could have said about a sigma bond having the bond directly between atoms, whereas a pi bond is above and below the plane of the atoms. Or you can mention electron density here. So for a sigma bond, electron density is between the two atoms. For a pi bond, electron density is above and below the plane of the atoms. So either of those there would have got you that mark. Right, it then says explain why compound A does not have EZ isomers. So if you remember, the two criteria for EZ isomers is that it must have a double bond. That's the first one. And the second one is that each carbon in the double bond must be bonded to two different groups. And as we can see, this carbon here is actually bonded to the same group, and therefore it doesn't fit the criteria, and therefore it will not show EZ isomerism. So to explain that, I've said one of the carbons in the double bond is bonded to the same group, or you could have said one of the carbons in the double bond is bonded to two methyl groups. Either explanation would have been fine there. Right, the next one is to draw a structural isomer of compound A, which has EZ isomers, and it's asking you to draw the Z isomer. It's just asking you to draw the structure, so it's not stated whether to draw the displayed or the skeletal formula. It's up to you how you want to do it. So let's just recap what we mean by a structural isomer. A structural isomer is one that has the same molecular formula but different structural formula. So if we go back to A, the molecular formula for this is, so it's got 5 carbons and it's got 10 hydrogens. So that's the molecular formula. And that means our isomer must also have that same molecular formula. Over here, they've got the longest carbon chain, so 1, 2, 3, 4, or 1, 2, 3, 4. The longest carbon chain here is 4. So the kind of thing that you could do here is C5H10. You could do it as the longest carbon chain being 5. So that's one possible thing you can do. And in terms of where the double bond would go, because we know this has got to be an alkene because it's got to show EZ isomerism, so it does have to have a double bond somewhere. If I put the double bond at the beginning here, I'll end up having 2 hydrogens coming off here, which means it won't show EZ isomerism. Whereas if I put it here, and if I now draw everything else in, hopefully you can see that this molecule that I've drawn, so this is pent-2ene, this will show EZ isomerism because this carbon here is bonded to 2 different groups, this carbon here is bonded to 2 different groups, this group here all being what we call an ethyl group. So this will show EZ isomerism, and when it comes to drawing the Z isomer, the 2 with the highest priority must be on the same side. So I've just drawn this kind of displayed formula here. The 2 with the highest priority, so this one here, the ethyl group has the highest priority and the methyl group has the second highest priority. The hydrogens here have the least priority. If the 2 with the highest priority are on the same side, that makes it the Z isomer. So therefore this that I've drawn here is the Z isomer. What I've also done is done it in skeletal. So you could have done it as skeletal, or you could have done it as the displayed. It doesn't matter if you group it over here, that's absolutely fine as well. You don't have to show all the bonds because it hasn't specifically asked for the displayed formula. But again, this one over here, 1, 2, 3, 4, 5, it's still pent-2ene. And this one here is the Z isomer because the ethyl group and the methyl group are on the same side of the double bond. So you get 1 mark for the correct structure of the Z isomer, and the name is going to be therefore Z pent-2-ene. So 1 mark for the name of it. All right, next question. I'm just going to run through the kind of key parts of this question. So it's talking about compound A. It reacts with hydrogen bromide to form a mixture of 2 different organic products. It's then asking us to give the structure of the 2 possible products, then give the mechanism. So as you remember, mechanism is the curly arrows, and it's to show the formation of one of the organic products. So we have to show the mechanism for one. And then it says to explain which of the 2 products is more likely to form. So by that, it means which one's the major product, which one's going to be the one that is more likely to form. So what I'm now going to run through is where you can pick up marks. This is a 6-mark question, but there are more than 6 marks up for grabs. So I'm going to run through all the possible marks that you can have. So I'm going to start off by doing the mechanism part, which is this part here. So in terms of how the marks are allocated, you get 1 mark for this, for the dipole over here, so the correct dipole across HBr, and for having the correct curly arrow going from that double bond to the H delta positive, to the actual hydrogen atom. Okay, so that's a 1 mark there. Just remember, make sure you know where your curly arrows begin and where they end. Don't kind of have them a little bit wishy-washy. It must be from the center of this bond to this hydrogen atom. Okay. Next mark is for this bond here breaking. So again, the curly arrow must start at the middle of the bond, going to the Br atom, and that's your second possible mark. Next one is for drawing the correct carbocation. I've gone for this one. You could have equally have put the carbocation on this carbon and the hydrogen on this one. Either would be fine. So you get 1 mark for the correct carbocation. And the 4th mark that you can get in terms of the mechanism is the curly arrow starting from the lone pair on bromide going to the carbocation. Again, make sure it's starting from the lone pair going to the carbon with the positive charge. So there's 4 possible marks up for grabs when it comes to mechanisms, or this mechanism here. You then get a mark for the correct products. So one product is the one where the hydrogen's on this carbon and the bromine's on this one, and the other one is where the bromine's on this one and the hydrogen's on this one. So 2 possible marks here for the correct structure of the products. You could have drawn the products as the structural formula. You could have drawn the products as the displayed formula. You could have done it as a skeletal formula. As long as it's the correct product, that's fine. Okay, but molecular formula wouldn't work here because it's not showing the structure. Right, and the other thing that we need to do, so we've done the structures of the 2 possible products, we've done the mechanism to show one of the organic products, and we now need to explain which of the 2 organic products is more likely to form. So I've just labelled this one A and this one B, and A is the one that's the major product, and the reason for that is A is formed from this tertiary carbocation, whereas B would be formed from a secondary carbocation. And then you need to make a statement that a tertiary carbocation is more stable than secondary. And that is the other possible mark. So for me, saying product A is the major one, that's 1 mark. And for explaining why, that's the other mark. Okay, so there's a possible 8 marks up for grabs here. Right, this question here is about polymers. They're talking about 2-chloropropene, which can be polymerized to form poly-2-chloropropene, and to write a balanced equation for the formation, and the equation should include the structure of the repeat unit of the polymer. Okay, so start off by just drawing that monomer that we had at the top, and in terms of drawing the repeat unit, the double bond is broken now. Okay, the carbon is bonded to the same groups and same atoms as before. We now have these extending bonds, the square bracket. Okay, so you get 1 mark for this correct repeat unit being drawn. Your other mark is for balancing it by putting an N in front of your monomer and an N in the bottom right corner of your repeat unit. Right, the next one is about the disposal of this polymer. So they're saying about waste polymers can be disposed by combustion, and it's asking for one problem with disposal one problem of burning poly-2-chloropropene. Because this polymer contains chlorine, when you burn it, you will release hydrogen chloride gas, so HCl gas, and that gas is toxic. So you have to mention both of these points here to get the mark. So any polymer that contains chlorine, if you burn it, it will release hydrogen chloride gas, which is a toxic gas. So that's the problem for that one. Right, next one is about butane reacting with, so butane, which is an alkane, reacting with chlorine. So this is the halogenation of alkanes. And it's saying that one possible product is C4H9Cl. They've given you what the overall reaction is. If you remember the reactions of alkanes for halogenation, you need to have UV light. So UV, ultraviolet, you can even write sunlight as well, because sunlight is technically a source of UV radiation. Any of those would be fine for that. It then says to write the equation to show the mechanism of this reaction. So the first step is initiation. Initiation is the formation of the radicals, and this is technically where UV is utilized. So UV breaks that chlorine-chlorine bond to form two chlorine radicals. Propagation, if you remember, it's very similar steps for whatever hydrocarbon we're using. The chlorine radical plucks off a hydrogen from that hydrocarbon to form HCl, and then we're left with a radical on that hydrocarbon. So we've got C4H9 because the hydrogen's been plucked off, radical. This radical then reacts in the next step of propagation. So this is reaction 1 for propagation. This is going to be reaction 2. So C4H9 radical is going to react with another chlorine molecule, and that's going to pluck off a chlorine to form C4H9Cl, which is the product we're aiming for. And because it's plucked off a chlorine, we're then left with a chlorine radical. Okay, so the steps are always going to be similar. For propagation, it's always going to be a radical reacting with a neutral species to make a radical and a neutral species. So again, radical with a neutral species, reacting to form a radical and a neutral species. Okay, so that will always be what will happen in propagation steps. Right, it then says to write one equation for a reaction that would terminate this mechanism. So termination is where two radicals react together to form a neutral compound. So you could have picked any two radicals that we came across in this mechanism, reacted them together to get the product. So any of these would get you the mark here. Simplest one just being a chlorine radical reacting with a chlorine radical to form Cl2, but any of these other ones are possible. Right, the type of bond fission involved in the initiation step. So the initiation step is where we break the chlorine-chlorine bond. And in the bond, one electron goes to each atom, and therefore it is homolytic. So anytime we form radicals, it's homolytic fission. Right, one other possible product of this reaction between butane and chlorine is compound J. It then says to name compound J. Now I know we haven't done haloalkanes, but you do now know the steps of naming things. The only thing that you might not have known is that chlorine becomes chloro. Longest carbon chain, as we can see, just going straight through, 1, 2, 3, 4. It doesn't matter which side you number from because it's still the chlorine still form on carbon 2 and carbon 3. So this is 2,3-di, because there's two of them, chlorobutane. It then says to draw the skeletal formula of compound J. So there's 4 carbons in the butane chain. So 1, 2, 3, 4. Number them if you want. And the chlorine was coming off of carbon 2, and the chlorine was coming off of carbon 3. It then says, in addition to compound J, suggest one other possible structural isomer of C4H8Cl2 that could have formed in this reaction. Now remember, there's no control over which hydrogen is, plucked off. So it could be that the chlorine is anywhere on this butane chain. So what I've done is I've done it in the skeletal form. You could have equally have done it in the displayed form. I've just drawn all the possible combinations. So this one here is 1,2-dichlorobutane. This one here is 1,1-dichlorobutane because they're both coming off of carbon 1. This one here is 2,2-dichlorobutane, and this one here is 1,3-dichlorobutane. Okay, so any of those is fine. If you did it as the not structural, if you did it as the displayed formula, that's absolutely fine too, as long as it gives you this molecular formula here. So check your answer. Does it give you that molecular formula there? If it does, that's fine. Right, next one. Hexane reacts with Br2 in the presence of ultraviolet light. State this type of reaction. So the name of the mechanism is radical substitution. You need to have both of those words there to get that mark. If you wrote free radical substitution, that too is absolutely fine. It then says to identify the 3 possible structural isomers of the product C6H13Br that could be formed from this reaction with hexane. So essentially what you need to do is start off with a hexane chain. So 1, 2, I'm doing a skeletal, you can do it as displayed. So 1, 2, 3, 4, 5, 6. And then essentially you just need to place that Br in different positions. You could put it on carbon 1 and that gives you this one. You could put it on carbon 2 and that gives you this one. Or you could put it on carbon 3 and that gives you this one here. If you put it on this one, which is carbon 4, that technically becomes carbon 3. So it would be the same as this one. So they're the 3 possible structural isomers that could have formed in this reaction. They all have the same molecular formula. As I said, you could have done it as the displayed formula. I've gone for skeletal, but whatever you feel comfortable with, because they haven't asked you specifically what type of formula to draw. Right, next one. State the type of polymerization involved in the formation of polymer A. So if you remember, there's 2 types of polymerization. We've only looked at addition, so it's probably going to be addition. But the way to know is you look at this kind of chain over here, the backbone. This backbone is all carbons, and therefore it must be addition polymerization. If it had a backbone of another element, so if they had oxygens in there somewhere, that gives you a clue that it's not addition polymerization. It then says to draw a circle around the repeat unit of polymer A. So remember, a repeat unit, it's basically 2 carbons from that backbone. So pick any 2 carbons from that backbone. So I've just gone for these ones, and that there is 1 repeat unit. Okay, I didn't leave much space for this answer, but identify the monomer that formed polymer A. So if you just look at the repeat unit, essentially all you're going to do is you're going to break those bonds there, and you're going to form a double bond here. And that is what I have drawn here. Okay, this molecule here, so it's C2H5 here, so this is carbon 1, 2, and then carbon 3 and 4 are in this chain. So this here is but 1-ene. So that means the polymer that this is made from is polybut 1-ene.